In this video, we're going to relate the magnetic field, which is what we've been referring to as the H, to the magnetic flux density. Which we've been denoting with the letter B. So we're going to use a process similar to when we were coming up with electric field and electric field density, with the caveat that quite often the related material parameters is not always as straightforward as it is with electric fields, just with the way that magnetic materials work. So let's say we have a material and a magnetic field. So we have a magnetic field H. What ends up happening is that the magnetic field induces certain magnetic moments within the material. So we'll just use the magnetic moments. We'll use the letter M to denote the magnetic moment, and then we'll use chi M to denote the relationship between the magnetic field and the magnetic moments that show up. So we have a magnetic field, and then with our atoms, just simplistically in a simplistic model, we have atoms inside. The material will consist of atoms, and all of these atoms will have these little electron spins. And so for all intents and purposes, these act like very small current loops or regions of current. And so with that, as a result, there will also be all these different little moments that show up. So this is kind of the very rudimentary cartoon model. Now so there would be a relationship between the magnetic moments that appear in the presence of a magnetic field, which we will describe with the letter chi M. Now, one thing to remember is that chi M, it can be anything from a constant or a tensor. So in many cases, this is a little bit more complicated than with electric fields, but these can sometimes be described as a tensor, where the magnetic moment in a given direction is actually dependent on the magnetic field in a bunch of different other dimensions. And the way they interact, you would need a tensor to describe. So I think for the time being, just know that it's not always as straightforward as just being a constant, like it is in the case of polarization in electric fields. But for the purposes of when it's just a simple number, we can follow a process very similar to electric fields, where we can write that the magnetic flux density will be a combination of the magnetic fields plus the magnetic moments that are created. And so if we plug this equation, the definition of the relationship between the magnetic field and the resulting moments in, we'll get that the inside can be rewritten as H plus chi M H, and then we can pull out the H to get that the magnetic flux density is going to equal to 1 plus chi M mu naught H. And then in many cases, if this is something simple, if it's not some super complicated tensor, but just a simple number, we can call this mu R, or the relative permeability, to get that the magnetic field is going to be equal to some unitless relative permeability, the permeability of a vacuum, and then H. So this is the exact same as how the electric flux density in many cases can be written as a unitless relative permittivity times the relative permittivity of a vacuum and the E field. So these two are directly analogous, and where you have some unitless relative constant telling you how this changes from the situation in a magnetic field. So the basic take-home is that the magnetic field and the magnetic flux density is related by the permeability of the material, and in many cases this can be described as a relative permeability times that of a vacuum, mu naught, just like we do that between electric field and electric flux density. But the other thing to keep in mind is that this chi M is not always as straightforward, and so in many cases the magnetic properties of a material when it's significant is sometimes often a little bit more harder to describe than in the case of electric fields. But in most cases, and I would say that for the purposes of this class, a majority of situations that you interact with, the material, the magnetic properties will be similar to that of a vacuum. So mu r is quite often equal to 1. And if I don't specify in problems, quite often that's usually what the going assumption is. But in most materials, epsilon r has a lot of more variability. So I would say that in a large chunk of the problems, you just have mu r equal to 1 and epsilon r being equal to something else if you're not in the case of a vacuum.